There you go. Thank you.
Okay, these are our divisions. We belong to the Digital Solution and Platforms division. Our division deals mostly with SCADA software and like. We have many control center projects in the region, both TSO and DSO, mostly in electrical power, but also in gas and generation, some power plants. We use third-party solutions for control centers, mainly Hitachi, but also PSI. But we also have our own software for the EMS, that's NetVision, installed in Croatia. We have our own substation SCADA, actually 2 substation SCADA softwares. And we have some softwares for river basin control, for LFC, so automatic generation control and optimization of production. And some of our colleagues are members in ISC working groups which pertain to the SIM. So working group 13, 14, and 16, these are SIM for transmission, distribution, and markets. And some of our solutions are certified to various international standards, but CGMS is a variant of SIM prescribed by ENTSO-E for European TSOs. Okay, that's enough of the intro for the company. So we'll talk about a little bit about the SIM. Okay, the SIM is a common information model that's prescribed by the ISC, and it consists of 3 basic things. One is a model, that's the basic meta model that's developed in UML, in Enterprise Architect app by the working groups or standardization working groups. And that's the complete model, all classes, all attributes, etc. Then you have profiles that are subsets of this model for various use cases. And the serialization part, which prescribes a way to write this model data to formats for exchange, to messages or to files, mostly XML for now, but JSON is in the standardization pipeline too. Okay, so what is SIM? SIM is a common information model, mostly for electrical networks. Data exchange, it was made firstly for TSO data exchange for load flow calculations on the European level. As you know, European network is one complete network, but you have 40 TSOs which need to exchange network model data and some case snapshot data. As I said, it's developed by ISC Technical Committee 57. The main model uses UML to define the ontology. It defines some thousands of classes with attributes and relations with multiplicity, uses single class inheritance, uses UUID for unique identifiers, and it's extendable. So every TSO or DSO needs something that's not in SIM, and it can easily be extended. And this UML ontology, we call it the meta model. And the data that we exchange, we call it the model because it's a network model. So this is the actual data, and the actual data is in an RDF structure. So it can be modeled by triplets, like class instance has some attribute of some relation that is equal to some value or some reference. And this is the model. And SIM, as we talk about it, is often said to be an object-oriented model, but it's not only that. It can be interpreted as a relational or document or graph because you have a topology of a network. It also includes geographic data, includes measurement snapshots, some blobs like load curves, etc. As I said, every instance of a class has a unique ID, and these objects mostly correspond to physical elements of the electrical system, but also some more organizational elements or types, measurement locations, ownership, whatever. So all physical and non-physical objects in the electrical system and business. Okay, so the class hierarchy and attribute semantics are detailedly prescribed by the basic standard. So the basic SIM standard is a sort of a data dictionary for electrical networks. And as I said, it can be extended. When we talk about serialization, for now, it's mostly XML, like RDF XML, but a slight incompatible variant of RDF XML. But mostly it's a simple listing of objects with some attributes, and some attributes can be values or it can be references. we have profiles that are subsets of this model, and main uses are, okay, main use that we are focused on is model exchange. So you can exchange models between TSOs, DSOs, or various actors, but you can also use the SIM dictionary for messaging, for making, for example, REST web services, and you use messages in them that are formed according to SIM. And you can use the SIM in some wider meaning as an integration platform for EMS apps, DMS apps, etc. So it's sort of a platform for integrating modules in control centers mostly. Okay, I already talked about the working groups. You have three basic working groups and standards which pertain to the SIM. This is 61970, and that's the TSO network modeling grid part. It's the core SIM part, which defines the network model for those basic network calculations, some dynamic models, and some metadata exchange. And these are some packages that you can see on the picture. We have working group 14. This is mostly pertaining to the DSO and some business integration with some outside systems that are not just process control systems, so asset management, workforce management, etc. And we have the market working group that we are not really focused on. We don't deal with that. And these standards are different between Europe and America. The working group, these two standards, the network standards are shared and used in America and Europe normally, but the market standards differ because of different market structures. And these are all like abstract SIM standards that are done by the ISC. But one variant of these standards is standardized as CGMS by the NSOE, and it's mandatory for European TSOs and data exchange between European TSOs. And this is a really important use case. I would say the most important and the biggest SIM use case. And this is data model exchange between European TSOs for various network applications, as you can see in the list. And this is like a picture of data flows and various SIM profiles, how they interoperate and standards. So as you see, you have the core equipment model that's EQ. You have some extensions for short circuit, for connectivity, for topology. You have a diagram layout that's for single line diagrams, so pictures, SCADA pictures. You have transient models. You have boundaries. These are really physical country or TSO boundaries that you connect the models. So you need to connect these models. Everybody shares their partial model, and they all need to be connected in one European model. And you have these load flow, topology, state variable, and steady state hypothesis profiles. So this is just basic EMS apps and data exchange. And okay, why SIM? SIM is I would say the oldest model of this type in the electrical sector. It's widely used. It models most elements and processes which are within the electric sector, and really includes many engineer years of domain expertise and model building. And why use SIM? Because it's the best you have, and it's already made. You don't have to make your own model. And anyway, anytime you integrate two systems, you create an implicit some common information model. So why not use a common information model that's standardized? And today it enables interoperability with various standard software. So be it SCADA systems, some standalone network software, or GIS systems, workforce management, etc. It's used in America, it's used in Europe, and it's mandatory by NSOE for European TSOs. And really it enables modularity, so you can purchase some apps and integrate them into a control center solution partially. You don't have to buy everything from one vendor. You can phase your changes. You can incrementally upgrade and replace some models. And when I talked about SIM profiles, these are subsets of the model for some use case. It's basically a list of classes and attributes that you need for that class. That's a subset of the big SIM model. And when we talk about formats in which these profiles are distributed, two formats are used, either an RDF schema for R, standard group for TSOs, or an XML schema for the market and DSO standard groups. this is obviously not enough to validate the complete model, so various additional constraint languages are used. Most recently, it's Shackle, used for validation of exchange models. And profiles are various. So profiles are per use case, and the most important one is obviously equipment, EQ, but also you need topology, you need the load flow profiles, you have geographical layout, diagrams, dynamics, etc. When we talk about serialization, it's the way of rendering the RDF data into files. We have SIM XML. It's based on RDF XML and RDF schemas, but unfortunately, it's not compatible. I mean, it's mostly compatible with RDF XML, but the recommendations were not complete when SIM XML was made, so some incompatible changes were done. And we have JSON LD for the future. It's not yet standardized, but already some vendors have been implementing it, and it will be probably the future because XML is not that popular anymore. But basically, the data is the same, and nothing important changes. Okay, some important SIM concepts which are prescribed by SIM. So you have the document metadata. Every file, every message that you exchange can have metadata. Okay, with who sourced this data, when is the creation time, scenario time, description, etc. So regular metadata. All class instances are identified by UUID identifiers. So these are decentralized, unique identifiers. You won't have collisions in practice because 128 bits is a lot, and you can create them decentralized. You don't need a central authority to deal out IDs. SIM supports multiple names in various contexts. So, okay, you have one unique ID, that's UID, but this object is named whatever in the GIS system, it's named, it has another name in the SCADA system, etc. So SIM supports multiple names in multiple contexts. SIM supports universal network topology modeling via two classes, and this is really elegant. So you have connectivity node and terminal. Terminals are assigned to physical components. They have terminals, and terminals are connected to connectivity nodes. And that's enough to reconstruct an entire topology graph of the network. An important SIM concept is the PSR asset info. So you have, and this is not in all systems. In SCADA systems, commonly you only have the PSR. So PSR is the asset function. It's, you know, transformer number 1 in substation so and so. But when that transformer, for example, burns down, you replace it with a new one. It's still transformer A in substation so and so, but it has a new serial number. It's a new asset. So you need to differentiate between asset function or place and real asset that has a serial number, and the asset info, which is characteristics like nameplate characteristics, types, which in DSO use cases is important because they have like thousands of transformers with same characteristics. And DSOs, usually transformers are unique. Every one of them has its own characteristics. And okay, SIM is made for merging models. So you can have partial models which have references which are broken. They're not in the model. And you expect to merge multiple models to get a full model, to assemble these models. So this is all a workflow that's supported by SIM. You take the models of 40 European TSOs, you take the boundary models, the real country boundaries, and then you merge the models and validate if everything is correct, and then you can do a European load flow or whatever calculation you need. Okay, so why PowerCIM? Why did we make this platform? Because SIM is basically a data dictionary standard and a data exchange standard. So it standardizes the data itself, and it standardizes a way to exchange data, but it doesn't standardize really the way you integrate, and it doesn't standardize the way you persist the data to disk, the way you save the data. So how can you save the data, for example, and share it integrated? You can have a file server with these files. I mean, that's the easiest concept. You can have some message queue or enterprise service bus, so you can connect two systems and they send files through the enterprise service bus. But this is still too simple, and it's hard to use this data later. What we really need is some sort of repository, or as other vendors call it, network model manager, that's sort of a SIM database. So you can store these models for later use, not just have point-to-point connection between systems. And so you can have a single source of truth or a platform to build applications upon. And it's much easier because, as I said, with message queue and enterprise service bus, okay, you have assisted messaging, but you still have one-to-one communication between systems. It doesn't solve the important problems. It just solves the basically IT problems, not the real application integration problems. So this is a reason why we think we need a network model manager, and we're obviously not the only ones that have a software like that. So yeah, as I said, it's a single source of truth platform for exchanging network models. You can have unified access to SIM data from various sources. You can do versioning, so you can have all the old versions of model, which are really important, because if you want to have some historical calculation, you need to have all the historical models. Usually in SCADA systems, you don't have real support for this. You only have the real time, the most recent model. Maybe you can restore something from backup, but you don't have a real historical database of models, which really complicates some historical calculations. For example, in DSO, SAIDI calculations, you need to consider entire models and model changes throughout a year, for example. And the hierarchies, okay, most SCADA systems, GIS systems, etc., organize their data in hierarchies. And SIM doesn't define actually a default hierarchy, but you can infer some hierarchical order from the SIM data. And people like trees. People like to explore their data, their models through some hierarchy trees. And last but not least, we want this to be a platform for application development, so we can have a good developer experience, not to have every developer reinvent the wheel, need to learn the entire SIM standard, etc. So you can get the data that you need as soon as possible. And these are SIM repository features versus a usual service bus or file server or whatever solution. You can persist the data for later use, have a single source of truth, version it. You can have branching and Git-like version control system like branching, hierarchies, multiple names. You can have fast model querying. For example, I need a model that was active a month ago. I need to get it fast. I don't want to, search through old files, etc. I don't want snapshots of every model because these models are slowly changing data. So there's a little bit of differences added every day, every week, whatever. And it's not really optimal to store snapshots of this data every day. You need to store the differences, and then the data is much more manageable. You need to obviously validate your models if they're valid in whatever way, be it shackle, be it some specific validation, or to do a load flow that converges and gets good results. Okay, you need to import-export your data by SIM profiles, integrate other systems, and you need to have a platform for developing internal applications. And okay, on the inside, what is PowerCIM? Again, going back to the data, equipment data is slowly changing. You need to, construct a new tie line, a new substation, whatever, and you have a model. When you have a model with some number of objects, you will really not have that many changes. If you have 100,000 objects, maybe in 30 years, you'll have 100,000 changes, for example. So that means it's a relatively small data set if you store only the differences. And writes are really rare. You maybe update a model once per day, or maybe a few times per day, or maybe even once per week, but you read it frequently. So it makes for easy concurrency and easy scalability. And so we store only the changes and assemble the needed versions on demand. Okay. And the versioning that we implemented and that we are most proud of is bitemporal versioning. So you need to differentiate between time that you enter the data in your system and the time that this data is valid, because you can enter data today that a new substation is going to be built and put into working order a month from now. So you enter today future data, or maybe some data was incorrect and you enter it today, but you change it from 6 months ago. And you want to have this whole audit log, this whole versioning history, and you need bitemporal versioning. This is also not new. In some other sectors it's used, financial, etc. But we decided to use it in this use case. SIM has some support in metadata for this, but really SIM doesn't define this sort of versioning. SIM only defines the data dictionary and data exchange for a single model snapshot. It doesn't define how you store historical model data. We decided to store it by temporally versioning. And it allows for corrections in the past or future planning, etc. You have a complete audit log, you know when everybody changed everything. You never update your records in the database, you append all changes. Obviously, you need to sometimes squash the old changes, but that's all normal. It's not a lot of data, really. And when we first developed this, our use cases was mostly, okay, we need fast model retrieval and assembly. We need to do it fast. And theoretically, okay, we have a graph model that's network, you have triples, RDF, whatever, graph databases, yeah, perfect width, really good. But really, these databases are not that mature. They use specialized query languages, and complex processing is not done on the database layer. You have a separate topology processor, you have separate EMS applications, etc. All that we need from the database is get this model version fast. You don't want, really, it's not a social network that you need to do topological processing on the graph database. So we decided against it. We also evaluated some document databases like MongoDB, etc. But really modern relational databases have the JSON XML storage types, and we get nothing new from using a pure document database. You can also use relational databases, but build the model from the UML, generate a table per SIM class, use a strict schema, and then it's really hard to manage because you have thousands of tables, you have schemas that are too strict, data that cannot go inside before you change the schema, etc. All these problems when you use a strict schema and auto-generate a model, create tables from some UML definition. It's hard to manage. So we decided, okay, we use the most simple relational database open source that we can. We use Postgres. The data was put inside in JSON, so it's schemaless. Really, we do late validation via models. We do validation, but our database on the lowest layer can store any SIM data. Doesn't matter if it's not according to some schema. We made our core library and server in .NET Core. That's the backend memory cache and indexing and the versioning part. And we have the REST API for access, and it does high performance streaming and querying of the data. And we have a web viewer app that we mostly use for testing and administration because this is a machine-to-machine system. You mostly talk, GIS talks to SCADA through our repository. You don't need really your own front end. You don't enter data in our system. You enter data in SCADA, in GIS, whatever, but you can view the data as you will see in our app. And okay, some of these concepts we already went through. You can have multiple sources of data. You can make multiple branches, repositories in one repo solution. You have small changes. You only store the changes. You store the data according to type. So equipment data is different from geographical data, from snapshots, etc. You need to have storage that's for performance reasons. You need to have storage conforming to the type of data you store. You use bitemporal versioning, so you can store all the versioning you need. We use the relational database for persistence, in memory for querying. We transparently can change the SIM meta model version. So we are schemaless on the lower level. This only means you change the validation procedures. And okay, that's schemaless storage with late validation. As we said before, we have branching that's inspired by modern version control systems, be it Git, Mercurial, whatever. So you have branching. You can have, you use a production branch and then you branch it to your own private repository, make some changes, and then you can do calculations on this modified branch, whatever. So it's good for experimenting, good for having multiple sources, whatever. And in the end, what is this? What is our platform? It's a platform for data exchange, mostly model data exchange of SIM data. It's high performance. It has advanced versioning and filtering capabilities. It has a streaming REST API that doesn't use much RAM. So you don't pre-allocate all this. This data can be big, you know, model data, even for a small country like Croatia on the TSO level is some 100 megabytes or something like that. For a bigger country, it can be gigabytes. You don't want to pre-allocate in RAM for every query. You need to stream this data from a central source. And these are our components. You'll see it later. So we have a core library that we put in all the SIM functions that we can use to develop standalone SIM apps. And this is import export functions, indexing, shackle validation, etc. We're going to add topology processing and some additional algorithms. And we have a backend server that uses this core library to serve this data for REST API and really for apps that don't directly use the SIM standard, because when you have, for example, SCADA that expects SIM data, it will probably import 552 SIM XML files. But you can have a web app using the SIM data that uses the REST API directly. We have Postgres for persistence. We used it for initial implementation of this versioning schema, but the query optimizer was really too unpredictable and it was too slow. The complex versioning queries were too slow. So we decided to use Postgres only for persistence, and we do all the indexing, etc., in memory. The front end is a React web app with some MapLibre geographical views. It's used for browsing and really a test front end, not a data engineering app, because data is edited in source systems that give us all of this data. We've been basically doing it for a long time, but not with a lot of people. For now, we have a complete department, us 7, that are developing this solution. But before, it was mostly like a database for our reporting and putting in SIM data for some of our projects. And one of our first projects was our TSO. Then we had a basic solution that made the error of making a table for each SIM class, which was really not good. Then we quickly switched to a schemaless solution using document storage, so JSONs. And we added some features. And in the latest version, we added the in-memory query engine when the Postgres was too slow. We added the web viewer. We have some European projects, Test and HEDGE-IoT. We have some of projects in our TSO and DSO. And that's it mostly for now. This is some schema of some application platform made for our DSO, really, but it can be adapted to the TSO. So you have adapters that import and export data for applications. You have some admin services, some topology processor, validator, etc., internal services, and you have the repository itself with an API and with the database that stores snapshots, metadata, time series, whatever. Okay, as I said, these are our projects. Currently, we have a project in our TSO that we integrated with Hitachi Network Manager and our own EMS NetVision system. We are currently doing a migration for our DSO. We're importing data from the GIS systems, network data, for the future ADMS system. And we'll be using this instance for DSO internal app development. We had one EU project before. It's a test for TSO-DSO integration, and HEDGE-IoT now for integration really within a DSO for the DTR system, dynamic thermal rating system. So we have a GIS system, dynamic thermal rating system, some weather stations, and we put all this data in our repository, and it's sort of a data space that you can pull this data out. For example, our academic partners can pull it out for various calculations, etc. And we've done an optimal power flow RFI proposal for our TSO with our home Faculty of Electrical Engineering. They're providing algorithms, and we're providing an integration platform and connecting to all these SCADA, GIS, etc. systems. And okay, usage, these are some cool pictures. This is for a test, so TSO, DSO model exchange, basically, and snapshot. So snapshot for load flow calculations exchange. So you have like 6 branches, and which are dependent one upon another, and the versions in them, and you merge all this data for some calculation or whatever app is using this data. This is the NSOE use case, usual that NSOE does every day for day-ahead congestion forecast. So it gets the equipment data from every TSO. It has its own boundary data. It has steady state hypothesis, so day-ahead data for every TSO, and it merges all this data and does the congestion forecast and load flow to verify it. And this works already for, I don't know how much, years already. This is maybe the device, as I said, the biggest use case for SIM, most mature use case for SIM. Although SIM is used, for example, in the USA in ERCOT for a longer time. This was like, I think the first big use case for SIM was in Texas in ERCOT TSO. This is a workflow that that proposed for a Saidi-Saifi calculation app for our DSO. It uses GIS for the network data. It uses SAP for customer data in relation to the feeders. It pulls out network topology data, switch data from the SCADA and historical switch data from the SCADA, and it merges all of it in a year or whatever and does the Saidi-Saifi calculations. So it has a topology processor and historical model data and historical switching data. So you can do a true Saidi-Saifi calculation that's really correct to the last second. And this is hard in most SCADA systems because they don't have really a historical model repository. Okay, and now we can have the demo. So just for a moment to say, okay, we have a viewer app that displays the data in table form, and it has a query drop-down menus that you can put in, okay, this repository in this version in this time. So this is by temporal versioning. You have version ID and valid time. You have two version axes, two version parameters, basically. And you get a response, either a model snapshot, okay, what the model is at this version, or a difference. You put in two versions and you get a difference between these two versions, or all changes you also put in two versions and you get all the changes between these two versions. Even if some attribute changed multiple times, you get multiple changes. In difference, you only get difference between two versions, and all changes gets all changes between two versions. And you have some additional filters. Also, you can filter by SIM class, by name, by IDs, or by hierarchy. So parent, give me all the switches beneath this in this substation or whatever. And dependent models, you can pull in dependent data or not pull in dependent data for export.